AZ3D Print, a Tucson-based company, specializes in additive manufacturing solutions by using recycled powder to create 3D printed parts. AZ3D Print caters to many industries, from general manufacturing to aerospace. With this large audience, their way of manually transporting powder by using a scoop from these 55 gallons is not an efficient way, and as well as not a safe way to have the recycled powder exposed. AZ3D Print came to U of A looking for an efficient and safe way of transferring recycled powder with sustainability in mind.
Hundreds of pounds of powder are sitting in the drums unused, and our sponsor's current method of moving the powder exposes them to a high amount of powder particulates, which can be messy and potentially dangerous. Our product would be reuse this powder in an efficient, profitable, sustainable manner to utilize the byproduct of our sponsored 3D printing. Much of our system was created using the very powder, further showcasing the reuse and strengths of this method. Hi, I'm Batula Kalaf and I'm the industrial engineer in this project.
Hi, I'm Caleb Carrot. I'm a mechanical engineer and I took lead on the hopper system.
Hi, I'm Seven Gilbert and I'm the electrical lead as well as the procurement lead on this project.
My name is Brenna Allen. I'm a mechanical engineer and I took the lead on the transport system.
My name is Madison Miliori. I'm the software engineer working on this project as well as system lead.
My name is Carson DiMaria. I'm a mechanical engineer and I took the lead on the mixing system.
We are Team 25043, Powder Conveyance System for Sustainable 3D Printing. Since the fall, we have been working for AZ3D Print to design and manufacture a system to transport and mix and color the additives to HP PA12 GB powder. We've gone through many iterations with our design choices and development to have create a final system that is divided into 5 subsystems: transport, mixing, hopper, electrical, and software.
The idea was to use a cyclone dust collector to pull powder from the 55-gallon drums into a smaller 5-gallon steel bucket. This smaller batch size could then be moved to a tumbler where a color additive can be mixed into the powder. Once the color is homogeneous throughout the powder, it can be placed on the hopper, which feeds the powder to the 3Dvo to create the 3D printing filament. All of these are controlled with a user interface whose primary component is a Raspberry Pi.
For our system to work right, it had a few main jobs. It needed to contain the PA12 powder safely, mix and color evenly, and move the powder from a big drum to the extruder. We also had to track how much powder was in each part and let users control everything through a simple interface. Most importantly, it had to dispense the right amount of powder every time. These requirements guided how we built the whole system.
Going into this project, the primary design question was what method we were going to use to transport the powder from the 55-gallon drums in a way that fully contained the powder to limit its exposure to the environment. After a point design comparison considering powder transport using a chain, auger, or cyclone, based on the material properties and parameters of the project, we chose to use a cyclone to transport the powder. Our sponsors specialize in 3D printing solutions and offered to print the final cyclone design, but we faced a problem. We had to design a cyclone which would work with an efficiency of 97%. Based on research of high-efficiency cyclones, we determined the geometric ratios of our design. With these specifications from the vacuum our sponsors wished to use for the final project, we performed computational fluid dynamics of our final cyclone design to ensure that we would be able to meet the 97% efficiency requirement.
Our next point of design was the method to mix in color additives. Our sponsors previously used a rock tumbler for smaller batch sizes. We wanted to mimic this simplicity, which brought us to our current design. Since we wanted our batch size to be held within a 5-gallon bucket, we designed a large-scale mixer that would use a belt pulley setup driven by a motor to rotate the powder at a specified RPM until the color was adequately mixed. We had to verify that the motor we purchased would be able to produce enough torque to reach the rotational speeds required to avoid powder mixing issues such as centrifuging, slumping, and cascading behaviors. We chose an optimal RPM and torque using a MATLAB simulation, which let us pick the best motor for our project.
Our final mechanical system to design was the hopper assembly. We wanted to ensure that there would be no excess powder buildup, so that way the flow would not stop prematurely. The funnel was designed and then 3D printed by our sponsor at their facility. We angled it ideally to minimize the possibility of the powder building up and stopping prematurely. Our initial design used the gate valve. During testing, we discovered that this valve could not close while powder was flowing. We then looked into ball valves. That worked to close while the powder was flying.
The electrical layout for this system is designed to provide automated control for the transport and mixing systems while recording usage for future reference. After the functionality of the mechanical system became more concrete, the layout of the electronics just fell into place. At its core, I knew that we would need a microcontroller to run the program and some relays to lead to the motor and vacuum for automated control. From this, we added a touchscreen for user input and a load sensor to measure the weight of the powder as it is loaded. The rest of the system is just power distribution from there. This product will allow hundreds of pounds of unusable powder to be recycled into a useful material that can be used to manufacture new 3D printing solutions. We are honored to have this opportunity to design this product for AZ 3D print and future consumers.
Our design is simple and yet effective. It can be easily reproduced in other 3D printing facilities. We created a full set of documentation for the system, including mechanical drawings, electrical layouts, software code, and all other testing procedures. Everything is clearly labeled and organized so that possible consumers can understand it and rebuild the system without needing to start from scratch. We also wrote a user manual to help future users run the system safely and easily. Because the design is low cost and reliable, it has potential to be patented. That way it could be shared or even sold to other companies in the industry. We believe this system could be more 3D printing facilities reuse their powder waste and work more sustainably in the future.